Right now, there is a pair of shoes sitting in a metal box on a freight train somewhere in the Midwest.
Yeah.
And in 48 hours, they will be on your front porch. But to get there, those shoes will change jurisdictions, they'll cross regulatory boundaries, and shift between entirely different modes of transport.
All without a single human hand ever touching the actual shoebox.
Exactly. You click buy, and this incredibly complex, globally synchronized machine it just hums to life to make sure that product appears.
It's a machine we all rely on daily. I mean, we really do. Yet it operates almost entirely out of sight.
Right.
We expect the shelves to be stocked and 2-day shipping to be honored, but the physical reality of bridging the gaps between a factory floor in Asia and your doorstep, it requires a level of orchestration that is, frankly, staggering.
Which is exactly what we are opening up the playbook to examine today. We're looking at a stack of supply chain materials to really understand the specialized glue that holds global trade together.
It's going to be a good one.
Yeah. The overarching mission of this deep dive is to explore the mechanisms of multimodal, multi-stop, parcel and courier, and pipeline transportation.
The big four for today.
Right. We are getting into the specialized modes that bypass bottlenecks and, keep consumer costs from absolutely skyrocketing. So, okay, let's unpack this. Because to understand modern logistics, we really have to start with the ultimate relay race. I'm talking about multimodal transportation.
Multimodal. Or it's often referred to as intermodal transportation in the industry.
Right, intermodal.
Yeah, it's defined by combining 2 or more modes of transport under a single contract and a single bill of lading.
Meaning what exactly?
Meaning moving cargo from an ocean-faring ship to a transcontinental train to a regional truck, all governed by one administrative umbrella.
Oh, wow. Okay.
But the concept only works because of the physical hardware enabling it. The entire system is built around one historically massive innovation.
The standard shipping container.
Yeah.
I mean, reading through the sources, it hits you just how revolutionary this seemingly boring steel box actually is.
Oh, absolutely.
Because before the container was standardized, the industry relied on break bulk cargo, and it was just a nightmare of manual labor.
Completely. I mean, imagine a port in the 1950s, right? You had stevedores physically hoisting wooden crates of machinery, burlap sacks of coffee, individual barrels of oil out of a ship's hold.
Just one by one.
One by one. And manually packing them into the back of a waiting truck. It took weeks just to unload a single ship.
Weeks? That's insane.
The damage rates were astronomical, theft was rampant, and, the labor costs severely limited how far you could profitably ship a good.
But with containerization, the paradigm shifts entirely because the container itself is handled, not the cargo inside.
Exactly.
The box is sealed at the factory, and it never opens until it reaches the final distribution center. You eliminate double handling, drastically reduce terminal turnaround times, and fundamentally lower the cost of global trade.
It changed the world, honestly. And because of that box, carriers can build specialized equipment to hand the baton back and forth. The industry jargon for this equipment is, well, it's like a bizarre backyard zoo.
Yeah, I saw that. The terminology is definitely unique to the trade. Like, when you combine rail and road transport, it is heavily reliant on piggyback systems.
Right, piggyback.
You have TOFC, which is trailer on a flat car, where they literally lift the entire truck trailer, wheels and all, onto a train. Or you have COFC, container on a flat car, which is just the box itself.
And if you're moving goods by air and road, they call it birdie back.
Birdie back, right, yeah.
Water and road is fishy back.
It's so literal.
It really is. But I found the operational choices behind these combinations really intriguing. For example, moving containers between a ship and a truck. The sources detail LOLO versus RO.
Okay, yes, LOLO is lift on, lift off, right? Which requires those multi-million-dollar port cranes to physically hoist the box.
Exactly.
And then RO is a roll-on, roll-off, where the ship acts like a giant floating parking garage and trucks just drive straight onto the deck.
And choosing between LOLO and RO is a classic logistics trade-off. With LOLO, you're maximizing the density of the ship because you can stack containers 10 high.
But you need the massive cranes.
Right. You are reliant on the speed of the port's cranes. With ROO, you are trading that cargo density for pure speed and independence.
Oh, I see.
A ROO ship can pull into a less developed port without heavy crane infrastructure, lower a ramp, and the cargo just drives away.
It's all about finding geographic shortcuts, which brings us to the concept of the land bridge.
Yes, the land bridge.
If a company is shipping electronics from a factory in Shenzhen, China, to a market in Europe, the traditional maritime route goes through the Panama Canal, But those massive post-Panamax ships often hit capacity bottlenecks or face severe congestion at the canal.
This is where multimodal strategies rewrite the map. Instead of taking the ship through the canal, you sail the goods from Asia to the west coast of the United States. You offload those containers onto a double-stacked train, literally stacking them too high on a rail car. That train acts as a high-speed conveyor belt straight across the North American continent to the East Coast.
Wow.
Then you load the containers onto a second ship bound for Europe. You are using an entire continent as a physical bridge to optimize time.
It is brilliant, but I gotta say, my absolute favorite example from the text regarding multimodal optimization is the alliance between Tupperware and Procter & Gamble.
Oh, that's a great one.
The physical mechanics of how they pulled this off perfectly illustrates the constant battle between weight and space. So, Tupperware makes plastic containers. They were filling up their shipping containers entirely, like taking up every inch of cubic space.
But the load itself was incredibly light.
Right. In logistics terms, they were cubing out.
While Procter & Gamble was facing the exact opposite problem. They were shipping dense, heavy liquids and laundry powders.
Okay.
They were hitting the legal weight limit for a shipping container while leaving the top half of the box completely empty. They were weighing out.
So both companies were essentially paying to ship empty capacity. Tupperware was shipping unused weight allowance, and P&G was shipping empty air.
Exactly. So they teamed up to share the same multimodal containers. And the physical loading strategy is what makes it work.
How did they pack it?
They put the dense, heavy P&G liquid securely at the bottom of the container, establishing a heavy center of gravity, and then they stacked the feather-like Tupperware plastics in the empty space on top.
That is so smart.
They improved their overall weight fill from 55% to 85%, which the text notes saved them 17% in total lane costs.
It is a masterful application of economies of scale.
Truly.
By understanding the physical characteristics of their freight, they created a perfectly balanced container. But pulling off that level of optimization across a fragmented global network introduces massive administrative hurdles.
It does.
Because here's where it gets really interesting. In our relay race analogy, handing off the baton between a trucker, a port authority, a rail line, and another trucker seems like a recipe for disaster. Let's talk about liability.
Yeah, liability is a huge issue.
I read the sources, and my understanding is that the legal rules actually change as the box moves. But practically speaking, if a container is sealed in China, moves across oceans, rails, and highways, and then opens in Chicago with $1 million of waterlogged electronics inside, how do you mathematically prove whose jurisdiction the box was in when the damage occurred?
That is the multi-million-dollar question, and it is a massive pain point for the industry. You are dealing with a severe lack of end-to-end visibility. As you pointed out, liability limits fluctuate based on the mode.
Right.
A truck operates under domestic highway law. A ship operates under international maritime law, which has entirely different caps on financial liability per pound of cargo.
So if a carrier can't prove where the leak happened, who pays?
Usually, it results in complex arbitration where everyone points fingers at the other carriers.
Yeah.
Without seamless, universal tracking, which is rare because ocean carriers, rail networks, and regional trucking fleets all use their own proprietary, homegrown software systems.
So they don't even talk to each other.
Exactly. So determining the exact moment of failure is incredibly difficult. It forces shippers to carry heavy, expensive insurance policies just to cover the operational ambiguity.
So multimodal gets a massive 40-foot steel box across the ocean, onto a train, and into a regional hub safely. But you can't just drop a 40-foot shipping container at a local pharmacy or a suburban grocery store.
No, you definitely can't.
The problem becomes breaking that mass down for regional delivery without destroying your profit margins with warehouse handling fees. How is that handled?
That brings us to multi-stop transportation, also known in the industry as split delivery. This mode is generally utilized for what we call heavy LTL. LTL stands for less than truckload.
Okay, less than truckload.
A multi-stop payload involves a single truck holding cargo destined for multiple different drop-off locations, either for various facilities of a single customer or for several completely different customers.
And the primary goal here is to completely bypass the traditional break bulk terminal. Because in standard LTL, a truck picks up your pallet, drives it to a massive regional consolidation warehouse, unloads it, sorts it with other cargo heading in the general same direction, loads it onto a new truck, and then dispatches it.
Which is a lot of steps.
Right. Every single time a forklift touches that pallet, it costs the shipper money and increases the risk of damage.
Precisely. Multi-stop eliminates that intermediate warehouse step. The consolidation terminal is only used in the very beginning to load the trailer, and the loading process is critical.
It is exactly like packing a grocery bag, right?
Yeah, that's a good way to look at it.
If you buy bread, eggs, and canned soup, you have to pack the soup at the bottom and the eggs on top so they come out first. A multi-stop truck has to be loaded in the exact reverse order of its geographic delivery route. The freight for the last stop goes in the nose of the trailer, and the freight for the first stop goes right at the back doors.
That reverse sequence loading is essential. Once those doors close, it is a straight line to the customers.
I see the elimination of warehouse handling, but I have to challenge the efficiency here. Navigating a 53-foot trailer through city traffic to make 4 distinct stops incurs what the text calls stop-off fees.
Right, stop-off fees.
You are burning driver hours, you're dealing with docking delays at 4 different locations, and burning extra fuel. Where is the mathematical break-even point where paying those stop-off fees actually beats just paying a standard LTL carrier to handle it?
What's fascinating here is that the break-even point is actually quite favorable for the shipper, primarily because standard LTL rates have such high built-in margins to cover the massive overhead of operating those break bulk terminals.
I see.
You are paying a premium for a sorting service you might not even need. But beyond the pure cost savings, multi-stop offers a strategic advantage called diversion or reconsignment.
Which is mid-transit agility.
Exactly.
Okay.
Let's say a truck is mid-route, and a freak winter storm hits a specific region, causing an instant spike in demand for generators or road salt.
Okay.
Because that freight isn't buried in a sorting warehouse, a shipper can reconsign a portion of that multi-stop load while the truck is literally on the highway, diverting it to the area with surging demand.
Oh, wow. That's incredibly responsive.
If you are a mid-sized business relying on standard LTL, your inventory is locked in the system. With multi-stop, you retain a level of dynamic control that can physically save your quarterly margins during unexpected demand shifts.
So multi-stop handles commercial pallets beautifully. But over the last decade, supply chains have had to adapt to an even more demanding reality, the e-commerce explosion.
Yes, the Amazon effect.
Right. Delivering millions of tiny individual items directly to consumers' doorsteps, which transitions us perfectly into parcel, courier, and express transportation.
This is the domain of the integrators, companies like DHL, FedEx, and UPS. According to industry standards detailed in the sources, this mode specializes in shipments under 150 pounds, or roughly 68 kilograms.
And their operational cost structure is totally inverted compared to other modes. When you ship multimodal, you are paying for the physical real estate of the box.
Right.
With parcel carriers, you have relatively low fixed costs compared to building a railroad, but intensely high variable costs. Aviation fuel, driver wages, vehicle maintenance. When you use an integrator, you are paying for dimensions, weight, and crucially, you're paying a premium for time.
Time is the ultimate commodity in this sector. To facilitate next-day or two-day delivery across the globe, these integrators rely heavily on the hub-and-spoke model. A prime example highlighted in the text is DHL's massive hub at CVG, the Cincinnati Northern Kentucky International Airport.
So, what does this all mean operationally? Packages from all over the country fly into the central hub in Ohio. They are unloaded, run through high-speed sorting belts, and then loaded onto outgoing planes, the spokes, flying to places as far-flung as Anchorage, Bahrain, or Johannesburg.
Yep, it's a massive operation.
But I have to admit, I understand the math behind the hub-and-spoke model. You are trading geographic distance for freight density, but with aviation fuel costs constantly spiking, isn't there a break-even point where direct point-to-point flights become necessary again? Plus, you are creating a massive single point of failure. If a blizzard hits Ohio, doesn't the entire global network freeze?
If we connect this to the bigger picture, the density math heavily outweighs both the fuel premium and the weather risk. Let's break down the alternative.
Okay.
If DHL tried to fly direct point-to-point routes between every major city, say New York to Miami, Seattle to Austin, London to Tokyo, they would need to operate tens of thousands of individual flight lanes. Most of those planes would be flying half empty.
And that's expensive.
Very. The cost to fly a Boeing 7777 is roughly the same, whether it is full of packages or full of empty air.
So flying an empty plane bankrupts the system.
It does. By consolidating every single package at CVG, they drastically reduce the total number of flight lanes. Every plane leaving New York is packed to the absolute brim because it contains packages bound for Miami, Seattle, and Tokyo.
Got it.
They all go to Ohio, get sorted, and then every plane leaving Ohio is similarly packed to maximum capacity. They ensure total utilization of the aircraft.
What about the weather risk?
As for the single point of failure, they mitigate this by building secondary regional hubs. But the core efficiency of the model relies on guaranteeing that no plane ever takes off half empty.
It is an incredible logistical balancing act. Okay, so we've mastered moving solids. Whether it is a 40-foot steel container on a transcontinental train, a reverse-loaded pallet on a multi-stop truck, or a small cardboard box on a hyperdense FedEx flight, we know how to move discrete objects.
Right.
But what about massive quantities of raw materials that simply cannot be put into a box?
That requires us to look at an often unseen, highly specialized niche, pipeline transportation.
I found the financial metrics in this section of the text absolutely staggering. Pipelines are used almost exclusively for moving continuous flows of liquids, primarily crude oil, refined petroleum products, and natural gas, from extraction fields to refineries.
And the reason they exist boils down to a truly unmatched cost advantage.
Unmatched is the word. To put hard numbers on it from the text, if you load liquid freight onto a truck, the carrier earns an average revenue of 17.88 cents per ton mile.
Okay, 17.88 cents.
If you pump that same liquid through a pipeline, it generates only 3.4 cents per ton mile. It operates at a fraction of the cost of any wheeled vehicle.
And that extreme economic advantage stems from a completely unique cost structure. We noted that parcel carriers have low fixed costs and high variable costs. Pipelines are the exact opposite. They have astronomical, almost prohibitive fixed costs.
Because you aren't just buying steel pipe. You are securing rights of way across thousands of miles of private, state, and federal land. You are funding decade-long environmental impact studies, navigating local zoning boards, and then physically trenching through mountains and rivers.
Precisely. The barrier to entry is massive. But once the pipeline is finally in the ground and operational, the variable costs, the day-to-day expense of actually moving the liquid are microscopic.
You're just paying for the pumps, basically.
You are essentially just paying for the electricity to run the pumping stations located along the route.
But the mechanics of it fascinate me, because it isn't just one type of crude oil flowing forever. How do they move different grades of fuel through the exact same pipe without ruining the product?
They use a technique called batching. They will pump a massive volume of, say, high-grade aviation fuel, immediately followed by a batch of regular unleaded gasoline, followed by diesel.
Wait, they just touch? They don't mix?
Because the liquids have different densities, they flow together with only a very small amount of mixing at the boundary where they touch. That tiny mixed portion, called the interface, is simply siphoned off at the destination and re-refined.
Which is incredibly efficient, but I have to point out the glaring weakness here, a total lack of accessibility. I picture a pipeline like a giant, continuous, miles-long straw buried in the earth. It literally cannot move.
That's true.
If a massive new refinery opens 3 states away, you can't just detour a pipeline. They require offshore oil tankers or rail lines to feed them at the source, and fleets of trucks to distribute the refined product at the terminal. They seem incredibly rigid.
This race is correct. They have virtually zero flexibility regarding route or destination. However, for a continuous, uninterrupted flow of a high-volume liquid commodity, flexibility is largely irrelevant.
Oh, I see.
When the objective is to move millions of gallons of oil between 2 fixed geographic points every single day for the next 40 years, the untouchably low variable cost makes the pipeline a foundational asset. No truck or train will ever compete on price for that specific rigid job.
It really highlights that logistics is never about finding one magic vehicle that does everything. It is a beautifully choreographed dance of specializations.
Very well said.
If you look at the whole picture, you've got the global relay race of multimodal transport using standardized containers to bypass canals. You've got heavy trucks strategically reverse-loading multi-stops to bypass warehouses and stay agile.
You've got hyper-dense air hubs in Ohio trading distance for aircraft utilization to power e-commerce.
Right, and you've got cross-country steel straws quietly batching fuel beneath our feet at 3 cents a mile.
It is a marvel of human organization driven entirely by the relentless pursuit of efficiency. But as we wrap up this analysis, I want to leave you, the listener, with a final thought to mull over, drawn from a brief mention in the text regarding the future of these networks.
The technological leap.
Yes. The materials note that at advanced, modernized ports, the physical handling of those standard shipping containers is already transitioning to AGVs, automated guided vehicles, and massive robotic cranes that do not require human operators.
So the relay race handoff is being automated.
Exactly. And simultaneously, we are witnessing the dawn of UAVs, or parcel drones, tackling that final mile delivery for the integrators. So the question becomes, how soon until this entire multimodal chain we've discussed, from a robotic crane loading an autonomous ocean ship in Shenzhen, to an automated double-stack train crossing a North American land bridge, to a drone dropping a box on your doorstep, operates with zero human touch?
That is a staggering thought.
And if that day arrives and robots are exclusively handing the baton to other robots, how does that fundamentally change the massive liability and visibility challenges we discussed earlier?
Wow.
If an autonomous crane drops a container onto an autonomous truck during a storm, do you sue the port authority, the hardware manufacturer, or the software developer who wrote the algorithmic code?
The ultimate relay race, run entirely by algorithms, creating an entirely new frontier of legal jurisdiction. That fundamentally changes how I'm going to look at the logistics network the next time a package magically appears on my porch. Thank you for joining us on this deep dive. Keep questioning, keep unpacking the complex systems running the world around you, and we'll see you next time.